but yes. So, hi, hello. Welcome to section number 2. Woo. Um, our game plan for today, we have 3 kind of big like areas of content, which is like a lot, but also is less than section 1, which was like 5 or 6 different areas of content. So hopefully it'll be a little bit easier. Also, hopefully I will not go over. I've tried to budget the time a little bit more carefully. We're going to start off with frontier molecular orbitals and some MO theory things, kind of building off of what we did in the first lecture and section. Then our second big topic is acidity. And finally, we'll start to get into some of this like 3D aspects of molecule with chirality. Are there any kind of like logistical questions before we jump into things, or any questions about the game plan?
I do just have one question,
Yeah,
Cole. I'm sorry if I missed it maybe
no.
during the lecture. Did she say what the exam format is like for the online students? It's during the time,
To be
right?
so honest, I'm not sure. Like,
Okay.
I need to ask about it. My guess, my very much guess, is like I'm probably going to be on a Zoom with y'all, like proctoring or something.
Okay.
But also, like, I am in Georgia. The rest of the team is in Massachusetts, so I'm still waiting to hear as well. But also, it's a thing of like if you don't hear about that by like next section, send me an email and then I will like follow up on that with them and kind of get those answers. But that's a great question to be having.
That's good.
Yeah.
Yeah, just biggest question was like if it's I think it's during the same time, but I just wanted to confirm.
I think so. I think
Okay.
so. Yeah. Cool.
Cool. Thank you.
Yeah. Well, if you can scan the QR, a little like section attendance code for today. I think that the fun fact for y'all to fill out is like, what's a hot take that you have? So I do like read all the responses, and I do like just hearing a little bits and pieces from y'all and getting to know y'all over the weeks. So feel free to let me have it of your hot take. But and also for video watching folks, feel free to fill it out as well, and I can be like, ooh, who is coming to my section? I don't know. Yeah. Okay. Well, with that, I will jump into the first content area here. So, frontier molecular orbitals. We are piggybacking off of what we talked about last week with MO theory, with sigma, sigma star, pi, pi star, all of that. And there is this kind of class of molecular orbitals that we care a lot more about than all the others, because building those big MO diagrams is really good to kind of give you some general principles at the beginning, but we want to get to the point where you're not having to build those out for full molecules and everything. So when we are thinking about the reactivity of molecules, we care about the molecular orbitals that are called the frontier molecular orbitals. They're on the frontier of reactivity, and these are the HOMO and the LUMO. So my joke is always like you have to get really good at spotting homos for organic chemistry, and you also need to get really good at spotting lumos. So homos is the highest occupied molecular orbital. It's the molecular orbital that's highest in energy and has electrons in it. Versus the LUMO is the lowest unoccupied molecular orbital. It's the first one in your MO diagram that's just going to have a blank on there and is not going to have like electrons filled in. So in a reaction, the HOMO of one molecule can donate its electrons into the LUMO of another molecule and create a bond. That's the essentially the kind of big idea here. There's this donor and acceptor interaction. And what we have is if we have like let's say a HOMO that's like this energy level and a LUMO that's this energy level, they are not going to have as good of an energy overlap. Like when they come together to form a bonding interaction, it's going to do a little bit of stabilization. But if our HOMO and LUMO are at similar levels of energy, then we are actually going to have a much more stabilizing bonding interaction form between them. And so oftentimes we think of reactions as what's the gap in energy between our HOMO and our LUMO, and we want to get them as small as possible for that gap. So generally what that means is we want homos, like donors, that are high energy, and they can kind of start to meet the energy level of these lumos that are unfilled. And we want lumos that are low energy. And so essentially what we are going to do, instead of building full MO diagrams, we are going to develop a cheat sheet for ourselves of what are some good high energy donors that are likely going to be the HOMO for a molecule, and what are good low energy acceptors that are likely to be the LUMO for molecules. So with that list here, our good donor orbitals, first up we have lone pairs. So remember when we were talking about the energy levels of sigma, pi, non-bonding, pi star, sigma star? This non-bonding level is the highest energy level where we're actually going to have electrons in the orbitals. And lone pairs would be at this non-bonding level. They're not a chemical bond, they're not a sigma or pi bond. So lone pairs are really great donors. And our one exception to that is halide lone pairs, like on like fluorine, chlorine, bromine, iodine. They are not as good donors. You don't really need to know why for that right now. Like part of it is for like fluorine. The fluorine lone pair is fluorine super electronegative, so it doesn't want to give up its electrons as much and attack. And then for the other ones of the halogens, they're so big that it makes it a little bit less high energy. But again, you don't need to know the justification for that as much as lone pairs are great donors, except for on halides. Those are a little bit worse. And then our second good donor that we have are alkenes, carbon-carbon pi bonds. Because think about an alkene as you have two carbons, and in a double bond, you have essentially 4 electrons all occupying like the same general space. Like, of course, we have the like sigma bond between them, and then we have the pi bond kind of above and below. But this is a buildup of electrons in one spot. It is also like in our energy level, the MO that's right under non-bonding. So pi carbon-carbon bonds are also going to be good donors. Then for our good acceptors, we want our acceptors to be as low in energy as possible. And so looking at our empty molecular orbital categories here, the lowest level of energy that we can be at is non-bonding and be empty. And so this is typically going to be like an empty orbital, like a 2p orbital on a carbon or a 2p orbital on a boron. So this is exactly what we have when we have a carbocation. So when we have a carbocation, this carbon has an incomplete octet. It only has 6 electrons around it, and there is a literal empty p orbital. And that's going to be at this lowest level of energy possible for our unfilled. So that's going to be a great acceptor. Another good acceptor would be pi star because, hey, that's the next lowest in energy. And our one exception for this, which again, you don't need to know this right now, the why as much. Pi star carbon-carbon molecular orbitals are not great acceptors. So we said that this like carbon-carbon pi bond is a good donor, but its antibond is not a good acceptor. Part of that is in our antibond, a carbon-carbon is non-polar bond. Like both of them have the same electronegativities. And so it means the lobes on either side of the carbons are going to be a little bit smaller. Like they're all just kind of smaller. And we're going to revisit some of this drawing orbitals and talk about why something like a pi star CO would be a much better acceptor in a little bit. But pi stars except for pi star CC. And then the last good acceptor after we do our non-bonding, after we do our pi stars, we are looking at sigma stars. And specifically these sigma star CXs are going to be the lowest in energy of the sigma stars because those were the highest in energy of the sigmas, and it's symmetric. So questions about these good donors and good acceptors as our shortcut list for what we should be looking for in molecules instead of having to do the full MO diagram.
Yeah, are the star orbitals, pi star and sigma star, always going to be empty for our purposes?
For our purposes, yes. They are always going to be empty at our MO diagram. And if we do a reaction, sometimes what we might do is we might put electrons into a pi star or sigma star, but we'll talk about what happens when we do that in just a minute, okay? So that's coming. So these are good donor orbitals, and these are good acceptor orbitals, but these might not necessarily be the HOMO or LUMO of a molecule. They oftentimes can be, and this will give us our short list for what is probably the HOMO or the LUMO, but this is just telling us what are good donors, and that's probably going to be the HOMO and LUMO. We'll see that when we do an example here. So this idea of like in a reaction, species can be electron donors or electron acceptors. This, we talk about the donor acceptor orbitals as specifically where the electrons are or where they're going. But if we want to talk about the molecule as a whole, the molecule as a whole that is doing the donation, we call the nucleophile. And then the molecule as a whole that accepts electrons is the electrophile. And we often abbreviate the nucleophile with NU, electrophile with EL or E. And electrophile, it wants electrons. It's accepting of the electrons. The nucleophile, I feel like that one's harder for me to like when I'm like first memorizing it. It's like nucleus loving, and that translating to like donor in my head isn't as sticky as like electrophile wants electrons, so it's the acceptor. So these are terms for a whole molecule. And then one special type of reaction that we talked about in this lecture are acid-base reactions. And we are using the Bronsted-Lowry definition, which talks about the transfer of hydrogens, H+, between molecules. And so the nucleophile, the donor of electrons, in that Bronsted-Lowry definition, is going to be the base. It is the thing that is going to be like an OH minus that is going and attacking, it's donating, and it's going to get an H plus on it. And a lot of these like acid base labels are a little bit tricky because it donating and accepting, you're talking about hydrogens versus electrons. So I've tried to list that out here just to keep it straight. And then the electrophile in an acid-base reaction is called the acid. So that would be something like H3O plus, where you would have a base come donating, grabbing this, and then kicking off the electrons here back to the oxygen. So to kind of put it all in a summary diagram, we are going to be using curved arrows to show the flow of electrons from the HOMO of a molecule, which is going to be a donor for the reaction. And this donor orbital, the HOMO, is on the molecule called the nucleophile. And if it is an acid-base reaction, it's going to be specifically called a base. So like a base is a specific type of nucleophile. Over here, the accepting orbital where the electrons are going is the LUMO, which is the acceptor orbital, on the molecule, which is called the electrophile, which may be an acid if it's an acid-base reaction. So that's kind of just putting all these terms because it's a little bit vocab soup right now. With that, I'm going to have one more idea to just revisit some of the MO theory things that we saw last time before we do these 3 practice, which is where we're really going to see how to like work with these ideas. So first, we talked about like the shape of these molecular orbitals of sigmas and sigma stars and pi stars, and about how we have like the in-phase overlap. It's going to make kind of a bonding region for a sigma here. And then for a pi, it's going to be above and below. And these that are printed on here are for nonpolar bonds, carbon-carbon bonds, for example. But when we have a polar bond, like carbon and oxygen, it changes a little bit. So in our CO bond, the oxygen's more electronegative, so it has a partial negative, the carbon has a partial positive. And so what we have is in the bonding orbital, we are going to have a larger lobes on the more electronegative element. So it's going to be, instead of this kind of even loaf, it's going to be kind of a lopsided loaf here. Okay, that makes sense. Like the more electronegative is pulling the electrons towards it. And the thing that's, I think, weirder and not as intuitive is to balance out for that, the antibonding orbital is going to have larger lobes on the less electronegative atom. So this is what it looked like for the antibonding when it was nonpolar, just even carbon-carbon. But now, if it is polar, we are going to have these be much larger than these. So it kind of like compensates for it. But now let's use this idea, and let's say we had some nucleophile donor that was wanting to put electrons in this antibonding orbital, the pi star CO. Do you think it's going to attack the carbon side or the oxygen side, based on this picture? And feel free to either put in the chat or unmute. We only have 5 people, so like, I love hearing y'all talk. Carbon, yes, exactly. It's literally just a bigger target. So one, it's a bigger target. The second thing is it has a partial positive, so it wants electrons more than the oxygen, which is more partial negative. So what we do is the electron is going to go and it's going to attack the carbon side if we were to attack this carbonyl. But a key idea that I want y'all to get down, and so I've been dabbling in Pavlovian conditioning. I did this over the summer and it was kind of like fun little chance, and it's going to be way more awkward via Zoom because that's the nature of it. But one thing that you need to know is electrons cannot sit in antibonds for the purposes of our class. And so if we are putting electrons in antibonds, we are breaking the bond. And so the little chant that I do with the class normally in person is electrons in, antibonds make the bond break. And it's literally like a call and response of I do electrons in, antibonds, and then y'all do make the bond break, so on and so forth. But like the fact that I'm like wanting y'all to like ritualistically chant this is how big of an idea it is. It's really this idea that I don't want to leave you, because also look, if we are attacking this carbon and trying to make a new bond here, this carbon already has 4 bonds. And so we are going to have to break a bond in order to form this new bond. So we are attacking the pi star CO, we break that bond, the electrons go over to the oxygen. So what we have left afterwards is now this oxygen is going to have, it originally had 2 lone pairs, now it has 3, so it has a negative charge. And then we've made a new bond to our nucleophile that attacked. And this kind of like tracing where the electrons are going, the donor and accepting orbital, that is the bread and butter of what we're about to do with this practice. So I'm going to do it one more time. Sorry to be obnoxious, but I really want it in your head. Electrons in, antibonds make the bond break. I appreciate y'all. Thanks for being with me. So we have the first 3 practices are going to be predicting how 2 molecules are going to react. Which that sounds like a really scary thing, but MO theory gives us a tool to kind of narrow down our possibilities. So first off, what we're going to do is we are going to try to identify the HOMO and LUMO of each species. And to do that, we are going to use our shortcut list here. And so I will kind of take the lead more on the first one, and then I'm going to ask y'all to take more of the lead on the second and third one, but just to for y'all to see the process of what we're looking at. I'm going to look at molecule A here and look at what are its good donor orbitals. So I first check, are there any lone pairs? And well, I guess there is. There's a lone pair on carbon. And so for a donor, I'm thinking lone pair on carbon, which remember we indicate with an N for non-bonding and a subscript C for it's on carbon. Our next donor after that would probably be like a pi CC, but we don't even need to list that because we know that this one's going to be the better donor. It's higher in energy. Okay, then let's ask, what's a good acceptor orbital here? Well, do we have an empty orbital? No, we don't have a carbocation, so we're not going to have an empty orbital. Do we have a pi star? Yes, but it's a pi star CC, which we said is not really great. But hey, that's the best that we have. We don't have any sigma star CXs, where X is an electronegative thing. And so I think our best acceptor is probably going to be a pi star CC, which again we said is not great, but is what we have on this molecule. So now that is without doing that full MO diagram. And just by looking at that of what our good donors and acceptors are, we can probably with 90% accuracy say, this is actually not just our donor, this is our HOMO. This is the highest energy molecular orbital, and this is our LUMO, the lowest energy molecular orbital for this molecule. Cool. So we've done that with molecule A, now let's do the same process with molecule B. So in molecule B, do we have any good donors? Well, it's not written on there, but what do we have on molecule B that could be a good donor? Feel free to unmute.
The oxygen lone pairs?
Yes, the oxygen lone pairs, exactly. So, good donor, we have a lone pair in oxygen, and I don't see any other really good donors, so I'm prepared to go ahead and just make this even faster. I'm going to say that's probably our HOMO. That's our highest energy donor that we have. It's our only good donor from the checklist. Then our good acceptors. So, do we have an empty orbital? No, we don't have a carbocation. Do we have a pi star? Well, we don't have any pi bonds. We don't have any double bonds, so we can't have a pi star. And so our next best acceptor is going to be a sigma star C something. And here we have a sigma bond between carbon and oxygen. So the sigma star carbon oxygen is probably going to be our best acceptor, our LUMO. Okay.
Can I ask a stupid question?
No stupid questions. Come on.
Okay, so why the lone pairs from the oxygen? There are also lone pairs on carbons, right? On both of those?
So not these carbons. So these carbons, they have hydrogens on them. And that's just our notation. Yeah. We can abbreviate lone pairs on molecules that are neutral, But before we assume that there's a lone pair, especially for carbons in our skeletal structure, we assume that it's meeting its octet via hydrogens that are just not listed. So that's
Thank
it.
you.
Totally. So we've done our homo-lumo analysis on both of these, and now we need to do matchmaker, make me a match. We have to look at these two and say, is it going to be better for these two to pair up, or is it going to be better for these two to pair up? We need some sort of homo and lumo from the two different molecules to come together to react. And to do this, we are going to say, hey, which of these is a better donor and which of these is a better acceptor? Well, between a lone pair on carbon and a lone pair on oxygen, which is higher in energy? That's kind of tricky. But we had our like low energy like trifecta, our kind of factors that affect the energy level. And we said electronegativity. Wow, this word takes forever to write out. I might have spelled it wrong. I don't know. Electronegativity is one of our factors affecting the energy level of our MOs. And we said if it's more electronegative, it's lower in energy. So that means this carbon lone pair is going to be higher in energy. So this is going to be our better donor of the two. Then comparing our accepting orbitals, our different LUMOs, well, we said that the pi star CC was not a good acceptor. So even though this is a sigma star, it is going to be our better acceptor. And part of it, again, has to do with this kind of almost geometry constraint here of in a pi star CC, you don't have a big target on the electrons, and also you have a buildup of electrons. You have like 4 electrons there between the 2 carbons rather than 2. Whereas if we had something like a pi star CO, then we have that partial positive, we have a bigger target. So that's why a pi star CO would be a good acceptor, but pi star CC is not so much. So this is the pair that we are going to want to do for our reaction. So now I need to draw curved arrows to show this. So I'm going to start at the lone pair on the carbon. So that's where my arrow is going to start. But then if I'm going to put electrons in the sigma star, and I forgot to put the subscript CO, sigma star CO, well, we know the sigma bond for the CO is going to be right here between them. But the sigma star is going to be on the outsides. It's going to be here and here. It's like the out of phase overlap here. And just like we saw with the pi star, we are going to have a bigger lobe on the less electronegative atom. So between oxygen and carbon, oxygen's more electronegative, carbon's less electronegative. So we have the bigger acceptor lobe here on the carbon. So if our donor is trying to go and add electrons to this antibonding orbital, it's going to be attacking at this carbon here. And now when we are doing our like curved arrows and everything, we don't need to draw the full MOs, but I'm drawing it here just so you can see that and build a little intuition. But for a curved arrow, all we're going to do is we are going to go and attack the carbon here. Now, pop quiz. We put electrons in an antibond. What happens? The bond breaks. Exactly. So, because we are putting electrons in the CO antibonding orbital, we need to break the CO bond. And we are going to take the electrons that were in that bond and give it to the other partner, in this case, the oxygen. So now, when we're drawing what the product of this is going to be, we have all of the other atoms that we like didn't mess with. So this was all there. We didn't change anything. But now this carbon needs to be attached to this carbon over here. So I'm just going to label this with like an orange C over here. Oh, I don't like how I drew that. Give me 1 second. So this is going to be our orange carbon. Then we have one other carbon, and then we have an O minus. And it used to be that this oxygen was like attached over here to the orange carbon. But now we broke that bond. Electrons and antibonds make that bond break. And so this is what our product is for the reaction. Questions on this process? I don't know. To me, it feels like a fun little game. It's kind of like these are like little characters, and we're like learning how they like react and what their special moves are, and like, yeah. Okay. Well, if there are no questions on this one, let's look at example 2. So example 2, this would be one that would be kind of hard for you to predict on your own. So we've given you the product. But what we want you to do is figure out what are the donor and acceptor orbitals here and like draw curved arrows for it. So this all is happening within one molecule. This one molecule is becoming this thing. And so if it's all happening in one, we call it an intramolecular reaction. Whereas this one between two different ones is called an intermolecular reaction. So go ahead, tell me what is a good donor on this molecule?
The oxygen lone pairs.
Yeah, lone pairs. This is all in lone pairs I'm seeing. So our HOMO is probably lone pair and oxygen, right? That's our best type of donor. Great. Now, what's a good candidate for our acceptor, or LUMO? Please, yeah.
The positively charged carbon.
Yeah, like already we have a positive charge. We know that that probably wants electrons. And we know that when we have a positive charge on a carbon, that is like a empty 2p orbital because this doesn't have a full octet. So this is our 2p orbital on a carbon. Okay. Well, if we were to draw curved arrows to represent this change, we do an arrow from our lone pair into our empty orbital, which is just on the carbon. So we draw our arrow literally to the carbon. But really what's happening is, again, we have an empty p orbital like this, and this lone pair is coming around and going and attacking. But again, for the purposes of like drawing curved arrows, we want to know, does it go to an atom or does it go to a bond kind of thing? So I don't know about you, but just looking at this, I'm like, that seems plausible. But how can I be sure that this is specifically what the product is? And also, like, how could I have like started developing skills to be able to predict this without the product being given to me? So what we do, a really powerful tool when we are doing intramolecular reactions often make rings. And so let's just count all of the like carbons or all the things that are coming together that should be forming a ring. So like this oxygen is going to be 1, this carbon can be 2, 3, 4, 5, 6. And I'm connecting this oxygen to this carbon. So that should form a 6-membered ring. And lo and behold, what do we see over here? 6. Okay, well now if I'm trying to map this onto the product, like I'll maybe do it as if I'm drawing it for the first time. So what I would do is I would just draw a 6-membered ring with an oxygen, and then I would just start numbering. So I'm just going to start numbering 1, 2, 3, 4, 5, 6. And if you are building it, if you are not beholden to a structure that's already printed on a page, you can number it either way, and it's just whatever works for you. But now what we need to do after we have this core ring is we need to get all the other like dangly bits that are on this. So like, for example, the oxygen, it has something else on it. It has a hydrogen. So we need to make sure we have that hydrogen. Carbon 2 has a methyl hanging off of it. So we have a methyl. 3, 4, 5 are boring. 6 has 2 methyls off of it. And what do you know? That's our product. Wow, we verified it. Feels like we've done like a mathematical proof. So this like numbering carbons is going to be a strategy that you'll see come back several times, and it's going to be important kind of moving forward. Cool. Questions on this before we go to practice 3? Yeah. Okay. So this one's a little bit harder. So this one, it is going to react 2 times. So we need to do our process twice in a row. Let's do it. So throw out, what's a good donor on this molecule? Anyone can take a stab at it. There's no like shame in getting things wrong as you are learning. So anyone want to be like in the hot seat who has not done it before to just like work through some ideas? I promise I won't bite your head off.
Is there a lone pair somewhere?
So to check, we only have carbons here, And so when we only have carbons, we're still using our skeletal structure rules. Everywhere that we are missing a bond is a hydrogen, not a lone pair. Because if we had a carbon with a lone pair, it's typically going to be looking like this where it has a negative charge. And because we don't see any charges, but I'm not going to let you off the hook if you will work with me a little. So we don't have a lone pair, so what's our next good donor to look for?
Are we gonna do something with the bond?
Yeah, exactly. So our second best donor is an alkene. So a pi CC. So our pi CC is probably going to be our HOMO. And then for LUMO, do we have an empty p orbital? Like, do we have a carbocation? No. Do we have a pi star?
No.
Well, so this is the thing. Our check for if we have a pi star is, do we have a pi bond? Because if we have a pi bond, we have to have its antibond too.
Yes.
So it's probably going to be the pi star CC. Now, we said that's probably not a really good donor, but it is still our best donor on this molecule because everything else is just like sigma star CC or sigma star CH. So nothing else. So that's great. Thank you. Is it Gabrielle?
Yeah.
Work. Thank you, Gabrielle. Does someone else want to be the volunteer for this other molecule for the thinking
brave.
through? No, please. Again, taking organic chemistry is a brave thing to do, so y'all are already being brave by like being in the room. Anyone else want to volunteer to be for the second molecule? Also, Risa, I just saw your messages in the chat. You can be the volunteer in the chat if you would like, if you do not have like camera mic things easy. Ooh, HOMO is a lone pair in chlorine. Beautiful. So we look for lone pairs. We have 3 lone pairs here. So lone pair on the chlorine, that's our HOMO. And then LUMO, accepting orbitals. Well, we don't have an empty orbital. We don't have a pi bond, so we can't have a pi star. So given that, what do you think our acceptor orbital is going to be?
Sigma HC. I'm sorry, I have babies crying.
No. Thank you so much for engaging. I appreciate it. You're totally right. The LUMO is going to be the sigma star of HCl. And honestly, it's going to be because that's like the only other option. Like, this is such a small molecule that we don't really have a bunch of different options. Okay, so now we've done this out. Now let's see, okay, which is a better donor? A lone pair in chlorine or a pi CC? Well, we said the lone pairs on halides are not as good donors. So the pi CC is going to win as our better donor. Then we compare the LUMOs. Which one's a better acceptor? Well, we said that the pi star CC is a good acceptor, the pi stars are good acceptors except for pi star CC. So given the choice between the two, this sigma star HCl is going to be better. And again, a lot of this might not feel super like scientific quantitative because we're kind of doing vibe checks, but like that is actually what we want you to do. We want you to develop a chemical intuition for how these molecules react. And just having this like short cheat sheet gives you a lot of intuition actually for how these molecules are going to behave. So let's donate the electrons from this pi CC into the sigma star HCl. So our arrow is going to start at the pi CC, starting from just the bond. And our antibond, we're going to attach the less negative element, attack the less electronegative element. And so we are attacking this H. Now we put electrons into antibond, so what has to happen? The bond breaks. So we are going to take the electrons in this bond between H and Cl and move them onto the chlorine. So now that we have our arrows, let's put it all together, see what happens. So we had this molecule originally, and then the electrons are going to go and form a bond with a hydrogen. It's going to grab a hydrogen. And maybe one thing I'm going to do is I'm going to color the arrow and show what that turns into in the structure. So the electrons in that arrow turned into this sigma bond between a carbon and a hydrogen. And then the electrons in this second arrow turned into a fourth lone pair on chlorine. Okay. Well, one last step when we are drawing these like new molecule transformations that we have, and I should have done it up here, I actually have a small error over here, is we have to ask ourselves, do we have any formal charges that were created by this? So like up here, we wound up with an oxygen with 3 bonds. That oxygen's going to have a positive charge, and it's reflected in this final structure, so not too big. But look at this carbon right here. Initially, it had a hydrogen, it had a double bond, and another bond to a carbon over here. But now it only has one hydrogen, bond, and bond. And so when this pi bond went in and attacked, we essentially stole electrons from this carbon. So because this carbon, and I'll draw in the hydrogen just to like make it a little bit clearer, because the carbon only has 3 bonds, we have a carbocation that was formed here. Because we have like taken away 2 of its electrons that it was relying on for its octet and made a bond over here with them. So that we've done step 1. We've correctly generated the product of the first step, and now it's saying that these 2 molecules are going to go on and react again with each other. So maybe let's start with the chlorine over here. Donors for it, well, literally the only thing it has is lone pairs. So our HOMO over here is going to be a lone pair on chlorine. We said that's not a great donor, but in the absence of literally anything else, it's what we have. And then for the LUMO, we don't have a LUMO. Like, I'll just do like not applicable. In fact, we don't even really have molecular orbitals. This is literally an atom. So it kind of feels weird to use MO theory here, but the framework can still work. Because here we don't have any molecular orbitals, so we don't have any acceptor orbitals. And remember, this non-bonding, this is an atomic orbital, a lone pair. Okay, well, if we only have a donor over here, we don't have an acceptor, then we need to find what's the best acceptor over here. Talk to me. What do y'all think? What's the best acceptor?
sp3 on carbon.
Like on this carbon over here?
Yeah, the one with the positive charge.
You're so close. So it is the carbon positive charge, but that's not an sp3. When we have a positive charge on a carbon, it is just an empty p orbital. And so we would call it like a 2pc orbital. And the reason that we do that 2p is because from Gen Chem, like when we're thinking about like the quantum numbers and everything, it's on the second row of the periodic table, so that's energy shell 2, and it's a p orbital, this like empty orbital. So that is going to be our LUMO. Now, if we had to do a HOMO, just to guess, we don't have any lone pairs, we don't have any pi bonds, we only have some sigma bonds, and I guess it would be sigma cc, but this is like a very bad donor. Like this is just a carbon-carbon bond. It's really hard to break carbon-carbon bonds, sigma bonds. So this is really the only matchup that works. And we are going to have the lone pair on chlorine donate into the carbocation empty 2p orbital here. So our final product that we get out of this, we still have this same framework over here. And one thing I'm going to do that's going to feel a little sneaky, I'm not going to draw this hydrogen. And the reason I'm not going to draw it is because I don't have to. And in fact, I didn't even have to draw it here. I just did it to kind of like help us see. But remember, skeletal structures, we can imply any carbon-hydrogen bonds. Similarly, I'm not going to draw this hydrogen either. So we have this framework, and I now created a bond between chlorine and the carbon that had a positive charge. And so our final product over here is going to look like this. Woof. So, like, I mean, that's a lot to be kind of putting together all this MO theory. But this is kind of where we're going. And like this skill of like being able to quickly diagnose what the donors and acceptors are, figure out good homo-LUMO combinations, and then draw the curved arrows to be able to predict the products, that is where we are going with reactions for this class. So any last things on MO theory before we pivot away and do our first like hard pivot from MO land to acidity? work? Okay. So whenever I have to do a hard pivot in sections during the summer in person, one thing I started doing, which is a bit much, is I was like, we need like some sort of cultural reset to like shift our brains to something completely new and to be like, this is a new chapter. And so I had a soundboard where I was playing like transition music from like Disney Channel sitcoms, like the Hannah Montana, the ooh, oh, yeah. Or like the Seinfeld transition. So I might try to get that. I don't have it ready for y'all now, but I'll try to get that ready in the future for us so that we can facilitate these transitions. So I'm going to go somewhat fast because I know y'all have seen acidity a lot in or Gen Chem. And I just really want to kind of talk about how do we adapt the things you already know for organic chemistry, the ways it's going to be useful. So in Gen Chem, you did a lot with Ka. We do not care about her. Our acidity measure for organic chemistry is pKa. So the trend is lower pKs are stronger acids. But the question that kind of remains, what do we mean when we say a strong acid or a weak base and things like that? So if something is a strong acid, it is reactive. It means that it really wants to give up a hydrogen. If something is a weak base, for example, and this applies like for both the strong base, strong acid, kind of you can make the analogous statements, but like a weak base is a base that is stable. So weak just here means not very reactive, stable. And typically what that means is if it's a stable base, it can handle electrons or a negative charge really well. So one thing that I always write on my paper anytime I'm doing acid-base questions is I write SA equals WCB. Strong acids have weak conjugate bases. That's kind of the short version. And you can also have the flip statement as well. And it's just a trend to remind me of things. A lot of acid-base things that we do for organic chemistry can feel sometimes like doing mental jumping jacks or gymnastics because we're not doing all the math. We're not doing all the calculations. And so we need to get to where we're kind of working with the ideas more. And it's sometimes hard to compare actual acid strength. And so what we do often is instead of comparing acid strength, we look at the stability of the conjugate bases. So let's see this with a kind of little face-off here. Now, I don't know that, did Serenia mention Cario as like an acronym for these trends in lecture? I don't think she did. And if she didn't, that's fine. Honestly, I hate it, but it's so like pre-medi and like it's like one of those pre-med, oh, my Cario, my acidity factors. It's a way to remember all the different factors that affect acidity. So Cario stands for charge, atom effects with electronegativity and atomic radius. R is resonance, I is induction, O is orbital effects. So Cario is the phone. Hashtag Dr. Life, hashtag pre-med, hashtag Orgo Schmorgo. But it's the thing that like I think it is a helpful tool for you to remember, but it's not like the be-all end-all. It's not going to solve everything. But to demonstrate each of these, we are going to do a little face-off between two small like chunks of molecules, and we are going to try to determine which is the stronger acid. So the way I'm going to talk about this, and again, everyone has their own way of explaining this, so if you have another way that works for you, great. I'm just going to kind of talk you through mine. What I do is if I'm comparing the acid strength of two things, I look at the conjugate base. So I think about removing a hydrogen from it. So if I remove a hydrogen from this one over here, now we are going to have two lone pairs. We're going to have NH minus. So which do you think is more stable between these two? NH2 neutral or NH minus? Which one's more stable?
Minus?
Well, this is the thing. Like, if you have the option of being negative charged at all or being neutral, it's going to be more stable to be neutral. Like we did talk about electronegativity in terms of being able to take on charge, and we'll see this in this next one, the more specific electronegativity focus. But if you have the option of being charged or uncharged, the uncharged one's going to be more stable. So this is the more stable conjugate base between the two. So it's a weaker conjugate base, which means this is the stronger acid. So another way that you can think about it is like this NH3 as an acid, it has a positive charge versus the neutral one. It wants to give up its hydrogen to become neutral. It is charged. And so that's another way to think about it. But I like this comparing the conjugate bases because it works in a lot of different scenarios. So that is the charge effect. having a positive formal charge makes you more acidic. That's our kind of takeaway from it. Let's compare these two. So if I draw the conjugate bases of these, I have NH minus and I have O minus. So now we don't have this like one is neutral, one is negative. They both have negative charges, which is not great. And so then we ask, who can handle the negative charge better? Oxygen or nitrogen? What do y'all think? Ding dong, I see an O in the chat. Yes, so oxygen is more electronegative, which means it really likes hugging onto those electrons. So this one's going to be the more stable conjugate base. In other words, it's the weaker conjugate base, which means this is the stronger acid. And so the pK of this, like an OH, is going to be like 14 to 17, whereas the pK of just a general NH2 is going to be like 30 something. And so our takeaway, so we don't have to do this every time, is between these two, the thing that has more electronegativity is going to be more acidic. Now, important note for this atom effects, this electronegativity rule is only between atoms in the same period or the same row of the periodic table. Like nitrogen and oxygen are horizontally next to each other. But if we compare atoms that are in the same column, like between oxygen and sulfur, then a different effect is happening. So in this case, the atomic radius is going to have a bigger role. So imagine you have a negative charge stuck on an atom, and for oxygen, you have like a little ball here, and that's like the atomic radius of oxygen. It's this kind of space. But then sulfur is much bigger. Sulfur, we are spreading out our negative charge over like a beach ball. So if we have a negative charge, do you think it's going to be more stable to spread that negative charge out over a big beach ball so it's like less concentrated? Yeah, it is, compared to the oxygen negative charge, which is on this like smaller contained space. So because of that, this is going to be our more stable conjugate base, which means it's our weaker conjugate base and our stronger acid. So a thiol, for example, has a pK of like around 8, whereas like an alcohol, it's again 14 to 17. So a lower pKa for this sulfur means it's a stronger acid. And our rule takeaway is the larger atomic radius wins when they are in the same group or column of the periodic table. Moving on to resonance. So we draw our conjugate bases. On the left, we have the opportunity for resonance. So we can donate in, push electrons over, and then that is going to spread out our electrons over all three of these atoms. And it's a similar idea to big atomic radius. If we can spread out a negative charge, it is more stable. So this one on the left, because it has resonance, it's more stable. So this is our weaker conjugate base, which means this is a stronger acid. And over here, we don't have any pi bonds, we don't have any p orbitals. They're like, we could delocalize in, so we don't have resonance. We can't spread that out. Then we have this idea of induction. So, O minus versus O minus. So, induction, my description of it is it's when you have specifically halogens on a molecule, things that are really electronegative, what they are going to do is they are going to be just tugging electrons towards them just a little bit. Imagine like the whole molecule is covered in this like electron cloud around it. Because like we use orbitals to show kind of generally where things are, but then just generally there are electrons around the whole thing because of all these orbitals. And I imagine like induction is you're sharing a blanket with someone and then they tug the blanket a little bit away. Because they are going to tug those electrons a little bit towards them. And so what happens is when we have fluorine over here, they are going to be pulling some of the electrons towards them. And that tugging of electrons helps to spread out just a little bit this negative charge. Now, it's not as good as resonance. Resonance is like, hey, we are going to fully spread this out over these three atoms. We are going to really delocalize these electrons. Whereas this is just a tiny little tugging on the electron cloud, but it does have an appreciable difference. So this is what we call induction, and it is going to make this a more stable base. So this is our weaker conjugate base. So this one is our stronger acid. And last one here. If we draw our conjugate bases, we have a negative charge on carbon in both cases. But what's the hybridization of this, this atom right here? How many electron domains does it have for the carbon? Oh, yes, thank you. Also, is it Risa? Yes, Risa, beautiful. Yeah, y'all are totally right. So it has 3 electron domains. This bond, this bond, this bond. 3 electron domains means it's going to be sp2 hybridized. And even after we take off one of these hydrogens, it still is only going to have 3 things. So it's going to have a lone pair here, it's going to have a hydrogen, and it's going to have this. So still sp2 hybridized. And then over here, this one's going to be sp hybridized. It's going to have 2 electron domains. One is this whole pi bond, and the other one is this lone pair. So this is the last one. How does like the actual orbital, a negative charge is in, affect stability? What we have is that more S character is going to be more stable. So like, let me see. We know that S is going to be spherical, right? So versus a p orbital, which is this like dumbbell shape. So if you think about the nucleus is positively charged, and so there is actually some electrostatic stabilization between negative electrons in the positive nucleus by holding the electrons close to the nucleus. So in an s orbital, you are just physically keeping the electrons closer to the nucleus than a p orbital, where it gets further out from the nucleus. And so when we say S character, if we look at something like sp2, this is 2 parts P, 1 part S. So this is 33% P, like 1/3 of it. Or sorry, I misspoke. 33% S. 1 of 3 parts is going to be S, the rest are P. Whereas in sp orbital, there are only 2 parts. It's 50-50, 50S, 50P. So this is 50% S. So this lone pair over here in an sp orbital, it's keeping its electrons closer to the nucleus, which is going to be more stabilizing. So this sp with a negative charge is going to be a more stable molecule. So this is our weaker conjugate base, which means this alkyne up here, carbon-carbon triple bond, is our stronger acid. And our general rule is more S character is more acidic. Now, when we are comparing just one factor, these rules work great. So like, again, if we just had the only difference between this is sp2 versus sp, the only difference between these two is resonance. The only difference between these two is atomic radius or electronegativity or something. Then we have these clear rules. But what if I was trying to say, okay, what's more acidic, this NH3 plus or this OH with resonance? That is a much harder question. And we don't have an easy way to compare between categories, which is why we use reference tables. And so over the summer, we actually require students to memorize these 10 pKa's just because it is going to be so helpful to have a frame of reference for these. You are going to have access on the exam to like the full document and everything. But honestly, if I were you, I would try to commit at least some of these 10 to memory, as these are probably some of the most important ones that you will see. And this just lets you know, like, okay, a nitrogen with a positive charge has a pK of about 9. A alcohol or water have pKs like 14 to 16. Just a normal hydrocarbon, like methane here, has a pK of like 50. That's crazy high. It's not acidic at all, really. And it just gives you a framework to be able to compare things. And this is for when your like rules, your Careo rules for comparing the acidity fail, or where there isn't just like one factor to compare between them. Okay. Questions on this before we jump into some quick practice? Well, one thing that I'm going to do really quick is just a brief comment on pKa and KEQ. So from KEQ, what do you remember about KEQ? Like, if KEQ is greater than 1, what do we know about a reaction? Greg Tucci is looking on at all of you, haunting you from beyond the semester. I would be happy to be haunted by Greg Tucci. Honestly, that sounds lovely. Any memories about what KEQ greater than 1 means? That's totally fine. So our KEQ, generally speaking... Oh, Frieza?
I was just saying reaction moving forward towards the products.
Product favored, yeah. So remember KEQ, the rough version of it is it's the concentration of our products at equilibrium over the concentration of our reactants at equilibrium. So if this fraction is bigger than 1, we have more products than reactions at equilibrium. So we are favoring a reaction going forward. Whereas if we have this fraction is going to be less than 1, it means the denominator is bigger. So that means that we have more reactants at equilibrium than products, so we're favoring this way. And then if k equals 1, it's not favored either way. So it's like equal product and reactant. So we have this handy dandy formula that lets us use pKa values and turn that into KEQ information to kind of predict which way a reaction is going to go between acids and base. So over here on the starting molecule, which do you think is going to be the better acid here? Or if you just look at this reaction, which of them gave up a hydrogen and became acted as an acid for this kind of forward reaction? Who's the acid? Yes, the OH over here. And also pop quiz on our functional groups. Because also I know we did functional groups and we moved on. Be memorizing those. They're going to come back in full force like lecture 4 or end of lecture 3. And it's going to be so helpful if you just know those down cold. This functional group is a carboxylic acid. It has acid in the name. So this is our acid. So using our table or potentially memorizing some values, we know its pK is 5. Okay. Well, then on the other side, that means this is the conjugate base. So that means if this was the base, this is the conjugate acid, NH4+, it has a pK of about 9. So looking at the pKa's of the acid on either side of the equation, we can use this formula 10 to the power of the pK of the product acid, which in this case is 9, minus the pK of the reactant acid, which is 5. That is going to give us our KEQ. So 10 to the 9 minus 5, well 9 minus 5 is 4, so this is 10 to the 4. Now is 10 to the 4 bigger than 1? Yes, it is. And so the reaction is going to favor the formation of these products over here. And so I think on the problem set you'll have 1 or 2 small things with this, but just a little brief connection. So moving on to practice number 4, ranking acid strength. So we have 3 ones to do, and if you downloaded the handout this morning, this first example has changed. Chris, I think, changed it a day or 2 ago, and I just didn't see it. So what we're going to do for each one of these is try to figure out which of our karyofactors is different between these hydrogens, and use that to tell us which one is probably going to be more acidic. So of charge, atom effects with electronegativity, atomic radius, resonance, induction, and orbital, what's the difference between the hydrogens on these 2 nitrogens in the first example? One has a positive charge. You're totally right. So, based on charge effects, this one's probably going to be more acidic by charge. Are there any other ones that we would consider here? Because they're both nitrogens, so it's not going to have a different atom effect. It's not going to be resonance because it's on the atom with the double bond. If it's next door to something with a double bond, there's resonance, but not when it's on the double bond. It's not really induction, but look at the hybridization. This thing right here has a lone pair, a hydrogen, and a bond, so it's sp2 hybridized. And this one over here is sp hybridized. It only has 2 electron domains. So this one also has more S character. So this is going to be the more acidic hydrogen. Work. In the second one, we have carboxylic acids on both sides. And so we're trying to look for a difference between these 2 hydrogens. And the thing that we have here is an OCH3 and oxygen. Well, this is not charge. It's not atom effects because they're both on OH. It's not resonance because they both have the same resonance here with the double bond. Induction. Is oxygen fairly electronegative? Yeah. And so typically we see inductive effects be talked about with like halogens, but it also is true for oxygens. So this oxygen is going to be tugging electrons towards it. It's going to be tugging electrons towards it here and here from all over the molecule. And so who do you think feels that inductive pull more? This OH that is 1, 2, 3 away, or the other OH, which is 1, 2, 3, 4 atoms away? Well, the one that's probably going to feel it more is the one that's closest to this thing. So this hydrogen is going to be our most acidic, and it's because it feels more induction. And I might put inductive withdrawal of electrons from the OCH3.
So essentially what's happening is that this oxygen is like pulling away the electrons that are bonding the hydrogen to the oxygen, which is why the hydrogen can like escape.
So again, I like to think about it in terms of the conjugate bases. So if we look at the conjugate bases of having, what if we had negative charges over here? It's basically like this is pulling more electrons away from this negative charge, which is spreading out that negative charge, making it more stable. So this negative charge, it was what would be more stabilized by the inductive pull of the OCH3. And you can view it in just the acid lens, but I find that that's a little bit harder, and like it's harder for me to personally explain too. Whereas if I think about, okay, look at the conjugate bases, which conjugate base is being made more stable, that is an easier question often for me to answer. Yeah. And the last one over here is a little bit harder. So we have 2 carbon-hydrogen bonds. They're both to carbon. And we do have like, this one's going to be sp2. This one's going to be sp3. So this one over here has more S character because this is 33%. Whereas in sp3, it's 3 parts P, 1 part S. This is 25% S. But there's something else going on here. So let's look at the conjugate bases. And I have a sneaky reveal. Are you ready for the sneaky reveal? Hopefully it's there. Woo! Yes, it is. So if we think about deprotonating here versus here, well, over here, we know that yes, there is resonance between these p orbitals and the pi bond, and these p orbitals and the CO bond over here. So we know that there's resonance between this, but this lone pair, when we deprotonate it, we deprotonate it from an sp2 hybrid orbital. And so that sp2 orbital is going to be perpendicular to all of these p orbitals doing resonance. So are we able to spread out this negative charge via the resonance? No, because it's not lined up parallel with all the other p orbitals. Whereas, if we deprotonate over here, we are left with a negative charge over here. It is sp3. It has a lone pair. And it is adjacent to a pi bond. So that was our neighbor rule that we saw from the first section. Of if it's sp3 has a lone pair, is adjacent to a pi bond or empty p orbital, it's actually not sp3. Once we deprotonate it and have this lone pair here, this is now going to be an sp2 hybrid atom. and it's going to put its electrons in the p orbital. And now when it does that, this p orbital is perfectly aligned to spread out its electrons and delocalize via resonance with the pi CO over here. So what we get is this one has resonance, whereas the other one does not. And so if this one over here, left one, wins with S character, the right one wins with resonance, who's more important? Typically resonance is. And I tried to kind of like star some of these effects here of like what's most important. And resonance is often going to be the biggest determinant here. So our most acidic hydrogen is going to be this one. And it's because when we deprotonate it, we are going to be able to delocalize this negative charge via resonance. That one's kind of nuanced. That's a lot. So sorry about that. Questions on this before we do our last hard pivot and talk a little bit about chirality with our last like 10-ish minutes.
I'm sorry, this might be a little bit off topic, but
No.
amongst those three molecules, how would we determine which one is the most acidic?
So if you were trying to compare across all of these molecules, much, much harder. And really what you would have to do is you'd have to use reference values. Like, for example, we know that the pKa of carboxylic acids is around 5. And then we would have to look up on our sheets, okay, well, hydrogen on a carbon-nitrogen bond, what's the relative pKa of that? And here, these, like, adjacent to a carbonyl, like, I think the pKa of this is, like, around 22-ish. But, like, that's where we have to use those standard reference values because these are such different scenarios between all the different molecules that we don't have a simple rule for it. Which is why when we're doing acidity ranking, we have to have the two things. We have to have this theoretical knowledge where we're comparing just one thing. And then also we have to have some reference values to give us an idea of the landscape. But that's an excellent question to be asking about this. And it's one that's just kind of a little bit beyond this right now. Like if I gave you the whole like big pKa table and all of these were listed, then yeah, you could just look up the pKa and determine it that way. But my hot take is I think it's going to be this one out of all of it. I think. But don't quote me. Cool. So, last topic, chirality. And again, we are in a whole different sphere now. So imagine the Hannah Montana music just played. Ooh, whoa, yeah. Some molecules. They have 3D structure. They are not these like flat things that we keep drawing. So let's think about these properties of molecules in 3D. So first off, we need some just basic definitions to lay the groundwork, I guess. And you're going to get a lot more definitions in the next lecture. So next lecture, she kind of split stereochemistry, which is this big topic about the 3D structure of molecules. She split it between the end of lecture 2, and it's going to be a bigger part of lecture 3. So you're going to see more of that on Thursday, which is why if you have model kit, have your model kit or bring your model kit with you. I would highly recommend getting it. It's like $20. And like it is the only way I have been able to effectively learn this. I'm going to teach you other like tools and shortcuts to try to do it, but really like building these and seeing it for yourself is how you learn this material well. So one note, if you are looking at like other resources online, like YouTube review videos or whatever, these definitions that we are presenting here vary a lot between classes. And so you might hear it used in a slightly different way in different contexts. So just bear that in mind. For the purposes of our class, a stereocenter is a tetrahedral atom, so like an sp3 hybridized atom, typically a carbon, that is bonded to 4 different things. So like, for example, one could be hydrogen, one could be CH3, one could be a CH2, CH3. This whole thing is different than that whole thing. It's about the wholeness of them, not just carbon versus another atom. And then like this 4th thing could be like an OH. So this would be a methyl, this would be an ethyl. 4 different things. Well, when we have a stereocenter with this tetrahedral geometry, 4 different things attached to it, it's a source of asymmetry in our molecule. So asymmetry is going to be important to us because it's related to a few different like physical properties of atoms, of molecules that you're going to see more in the next lecture. But one of the key features of having asymmetry is if you take a asymmetric molecule, like this one is attached to 4 different things, and you build a mirror image of it, So do you see how like it looks almost exactly mirrored? We have the wedges on the same, the dash on the same, but it's just flipped on the other side. If you build the mirror image and you try to rotate them around and put them on top of each other, you can't get the same thing. So like it's never going to lay perfectly on top. It's kind of like your left and right hand. If you try to superimpose, that's the like laying one thing on top of the other, you're never going to get your hands to exactly line up because your thumbs are going to be on the opposite side. But then look, if you look at it like this, they are mirror images over each other. They're non-superimposable. So this idea of a molecule having a non-superimposable mirror image, we call molecules with this property chiral molecules. And the main source of chirality, not having a superimposable mirror image, is having a stereocenter, because we said stereocenters are sources of asymmetry. So if we did not have a stereocenter, like look at this example, this carbon is not attached to 4 different things because these hydrogens look exactly the same. So if we take its mirror image and we try to superimpose it, we are going to be able to exactly overlap it. So here we did not have a stereocenter, so we have some symmetry in the molecule, and we are able to superimpose its mirror image. So in that case, if we are able to perfectly lay it on top of the mirror image, we say that the molecule is achiral. And so one really annoying thing, and I'm so sorry about it, is chirality means that there is asymmetry. Achirality means there is symmetry. I hate it. It's annoying, it's super confusing, and it seems like it's just there hoping for you to fail. But at least I want to like say this is the booby trap. It's right here. This is the like hole in the forest covered with leaves. So again, the big thing is chirality, this property of not being able to superimpose the mirror image, comes from having asymmetry, and our main source of asymmetry in molecules is going to be stereocenters here. So one of the first questions that we ask ourselves when we get to this stereochemistry unit, the like 3D structure of molecules, is we ask, is the molecule chiral? And so if we have 0 stereocenters, for the purposes of our class, we say it's achiral. If it's 0 stereocenters, then there is symmetry somewhere in it, and so we are going to be able to superimpose the mirror image. Golden. In different classes, they're like more complicated, like advanced examples where that's not always true, but for y'all, 0 stereocenters, achiral. Now, if we have 1 stereocenter, we have that source of asymmetry, so we know it's chiral. So we know we're not going to be able to superimpose the mirror image. If we have 2 or more, though, we have to do a check. So we have to check, is there a bigger picture internal plane of symmetry? So let's look at these 2 molecules here. They look very similar, except for in one of them, you have an OH on a wedge and an OH on a dash over here, and one where they're both on wedges. Now, it's not just the fact that one's on a wedge, one's on a dash. It's the fact that everything else is exactly mirrored. So you see this carbon is mirrored on this side, comes together, and then this OH is coming out on a wedge out of the page. It's coming out of the page over here, and the hydrogen's going back in for both of them. So this right here would be an internal plane of symmetry, even though both of these are stereocenters. This carbon is attached to 4 things, the OH, the H, the CH3, and this other carbon over here. So it has stereocenters, which normally would be like, okay, that's chiral, but because it has this larger internal plane of symmetry, we say it's actually achiral because there is that symmetry. And specifically, it has this special term that's called a meso compound. And meso, thinking like in the middle, there's a plane of symmetry, meso-middle. So over here, though, we have everything, these carbons are exactly mirrored, but one OH is on a wedge, one OH is on a dash. And so one's kind of coming out of the page, one's going back into the page, so it's not an exact mirror image. And so we would say, since there isn't an internal symmetry plane here, this is still chiral. It still has these asymmetry points. There's no symmetry on a larger scale. And so doing your rules, you check for stereocenters. 0 stereocenters is achiral. 1, it's chiral. 2 more, we check. And this is the thing. It's super easy to skip this check of just being like, oh, if there's a stereocenter, it's chiral. And so I think about like a sad little puppy being like, hey, what about me, Zoe? Don't forget me, Zoe. Which is really dumb, I know. But when you're taking the exam, you're going to be there and be like, okay, is it chiral or not? And you'll hear a little voice, which is my little voice being, hey, don't forget me, Zoe. And it's this check for meso compounds of this internal plane of symmetry. The other thing about checking for meso compounds is it's so much easier to do it with an actual model and just rotating your model to see it. And I think Serenia gave a good example of that in lecture where she like built it and she rotated it and saw it. So a quick example here, I'm not going to do both of these, but for this first one, it looks like this could have some internal plane of symmetry, right? Like we have a methyl, chlorine, and then there's a hydrogen on a dash over here. And then over here, we have a chlorine, a methyl, and a hydrogen on a dash over here. And it looks like because these have the same thing, they could be a plane of symmetry. But in order to really check it, we need to redraw this molecule or like build it and rotate it to specifically see if it's an exact plane of symmetry. Because remember, this looks like a plane of symmetry, but because one's on the wedge, one's on the dash, everything else is in the same spots, this is not a perfect internal plane of symmetry. So what I'm going to do is I'm going to try to get the same things in the plane. So I have the methyl in the plane over here. So I want to take this methyl that's over here and I want to rotate it into the plane like this. So this first carbon over here, I have not changed anything on it. So the chlorine's on a wedge, the hydrogen's on a dash. And then this carbon, I have to figure out what's on the wedge and dash over here. So I'm going to just draw the wedge and dash, but we don't know what it is yet. And I'm going to do some colors to help us out. So the methyl is the green, the chlorine is the orange, and the yellow. So essentially what I'm doing is I'm wanting to turn around this single bond. And when I turn around the single bond, I want to send this methyl to the position where the chlorine is. So if I do that and I move the methyl here in the plane, then what that's going to do is this chlorine is going to be sent around to the dash where the hydrogen was, because we're doing this one continuous rotation. So the chlorine gets put here, and that is our orange. And then our hydrogen would also get rotated around to be on this wedge where the methyl was. And so this skill of being able to rotate around a single bond, I think it's a valuable skill to be working on, like just practicing drawing on your own. But it's also something that, like, if you build the model, you can literally just twist it and you'd be able to see immediately. So now, when I look at this, is it meso? Like, is this an internal plane of symmetry for the molecule? Are all the wedges and dashes match? No. Exactly. And until we did this, until we wrote it out or until we built it to see this, we couldn't make that judgment call. Because, like, it's kind of like vibes of, like, does it look exactly right? I don't know. But here, this is not a symmetric plane. So, what would we say for this molecule? It does not have symmetry. It's asymmetric, so it is chiral. Whereas over here, if I do the same rotation, I'm going to do it a little bit faster just to save time. So if I rotate around this single bond and redraw this, so it looks like this. This Cl has stayed the same. The hydrogen has stayed the same over here. What we get is this is going to rotate and the Cl is going to be on the wedge. And it's a kind of a harder flip to do because here we did a 120 degree rotation. We just swapped where everything was. Whereas this, we're going from it being down in the plane to being up in the plane. So it's a whole 180 degrees. So it's a little bit harder to think about drawing. But when we do this, is this an internal plane of symmetry? All the wedges and all the dashes line up. So yes, this is symmetry. And so if it's symmetry, then we said that this molecule is achiral. Now, touching base with the 5 of y'all that are here, we've gone 7 minutes over because, again, I'm used to 90-minute sections. We have practice 5, chirality, which I'm happy to talk through and can like do here in the next like 8 minutes and finish at 7:30. Or we can call it down, and then like if you have more questions and things, we can go like you can come to office hours. Or also if you personally just want a piece, you can. But are there any of y'all that do want me to do this example with y'all? I'm getting a couple of, okay.
I feel like it's better to at least do the example because even if some people have to leave or whatever, everyone else that's watching the recording
Heard. My thing is just like, I hate to be disrespectful with y'all's time just because like I know like y'all are busy doing a lot of things. Many of y'all are like working, taking other classes, but also because it's recorded and it's a resource that you can come back to, and like there isn't pressure to leave here. I won't be offended or anything. Then let's go ahead and do it. And then again, I'm trying my best. I'm used to these. I've taught this for 7 years with 90-minute sections, and so I'm so used to the pacing of like full 90 minutes. But okay, for all of these molecules, we need to determine if it is chiral or not. And then if it is chiral, we are going to draw the enantiomer. So the enantiomer is the special name for if a molecule is chiral, like it has asymmetry, its mirror image of a chiral molecule, it's called an enantiomer. And it's one of these vocab terms that you're going to use a lot more in the next lecture. So it sounds kind of new now. I think she only mentioned it at the bottom of one page in lecture. She's going to come back. Don't worry. So the first thing I check for is, are there stereocenters? So in this first one, I'm going to look around for stereocenters. And this looks like it could be a stereocenter, right? Like there's a wedge, and wedges are often stereocenters. But is it actually attached to 4 different things? Well, the thing that's not written here is a hydrogen. This is a CH3, a methyl. This is also a CH3 here. So because these two are the same, like this is not a stereocenter. Okay, well, and then this carbon over here has 2 hydrogens on it, so it's not a stereocenter. So we have 0 stereocenters. Well, in our little flowchart, 0 stereocenters, we are achiral. Work. Okay, now in the second molecule, we look for stereocenters, and typically, like the good check is like just start off where there are washes. I almost said washes and dashes, dashes and wedges. So here, where you have wedges and dashes, just double checking this is an ethyl, this is a hydrogen, this is a ring. That's kind of boring for 3 carbons. This is a ring that then is going to hit this more interesting thing. So that still counts as 4 different things. So it is a stereocenter. The bottom one's a stereocenter as well. So we have 2 stereocenters. So if we have 2 stereocenters, we do need to think about, what about meso? But like, are these 2 stereocenters exactly the same? Do they both have an ethyl on it? No. So in order to really do this, remember, all the wedges and dashes need to be the same thing, like both here OHs. And so because like one of these is an ethyl, one of these is a methyl, we don't have to check for meso in terms of rotations and things because we know that it's not going to be perfectly symmetric. One has an ethyl outside, one has a methyl outside. So we have 2 stereocenters. So we are chiral. There's no internal plane of symmetry. 2 stereocenters, not meso. We are chiral. So now, drawing the enantiomer, there are 2 ways to do it, and they're both equal, and it's going to be hard for me to convince you that they're equal right now, so I'm not going to convince you. I'm just going to say a fact, and next section, we are going to do the proof of this and like prove it out. So there are 2 ways to draw an enantiomer. One way to draw the enantiomer is you draw the mirror image. And like that's pretty easy with a small molecule like this. You can draw the mirror image pretty easily. But once we get into like a big like chair, like ring structure like this, it's a little bit harder. And so the second option is you swap all the wedges and dashes and keep everything where it is. So again, I have not proven to you why this is true, but I'm going to use this fact that if we want to generate an enantiomer of a chiral molecule, all we are going to do is swap what's on the wedges and dashes. So for this bottom one, the hydrogen was on the wedge. Now I'm going to make the hydrogen on the dash. Then for this top right one, we had the ethyl on a wedge, so now it's going to go on a dash. So this is going to be the enantiomer. And this is the all swap version for our dashes and wedges. Versus the other one is our mirror image version. Again, both of them are equivalent. I haven't convinced you why, and we will see more of that in like lecture and section next time. Moving right along, down here, we have some stereocenters. This one, it has a hydrogen over here, and this one, it has a hydrogen over here. So we have 2 stereocenters. What do we need to check? Well, is it meso? So to do that, we have to redraw this, and what we're going to do is we are going to rotate around this single bond. So I'm going to try to redraw this to where my methyls are both going down like this. So when I'm rotating this, I'm keeping, this side is already down. So I'm not rotating this carbon at all. So I'm going to go ahead and put my wedge and dash there as they were. Then, when I rotate this around, I am moving this methyl from being up in the plane to being down in the plane. I'm doing a 180-degree transformation. And when you do that 180-degree transformation, if this methyl is going a little bit, or sorry, this hydrogen is going a little bit forward out of the page, and I do 180 degrees onto the other side, it's going to be going a little bit away over here. So it's going to be on a dash on the other side. And again, like this is just from moving physically. Like if we are moving this CH3 all the way down, let me see. I'm going to move this H up. I'm going to move this carbon down. And then I'm going to move this OH forward. I know that it's kind of hard to see with all this, but I swear building a model and just rotating it, you would see it really easy. So that hydrogen is going to be rotated 180 degrees. It's going to now be on a dash going away from us. And then that means the OH is going to be on a wedge. So now I check, is this an internal plane of symmetry? The OHs are both on wedges. The hydrogens are both on dashes. So yes, it is. So this is a meso compound. And so we say meso compounds have symmetry, so they are achiral. Last one. This one's brutal. They gave you a Newman projection. Ugh. So what we're going to do is the skill that we did last time, which is just translate this Newman projection into a perspective drawing to better see our wedges and dashes and things. So what I'm going to do is, this is my dot carbon in the front. This is my circle carbon in the back. I'm going to drag these so they are like this. They are horizontal. And what I want to do is I want to keep my methyl up like this and my methyl down like this. So this is the methyl up here on the dot carbon on the front. And then this is the methyl on the back carbon on the circle carbon going straight down. And when I've done this, what I'm doing essentially is I'm taking this front carbon and pushing it backwards here so it's in the plane. It's not coming out in front of the circle carbon, it's instead side by side. So when we do this and we're kind of rotating it backwards, both of these bromines then come to the front. So both of these bromines are going to be on wedges. And that means both the hydrogens are going to be on dashes. So now, asking the question, do we have stereocenters? Well, yeah. This carbon is attached to 4 different things: a methyl, a bromine, a hydrogen, and then this junk. And same with the other one. So we have a stereocenter there, we have a stereocenter there, we have 2 stereocenters. We have to check, what about meso? And I'm going to let y'all do the checking of that one on your own, but I will go ahead and tell you, this one does not have an internal plane of symmetry. If you rotate it around, it is not going to have a perfect plane of symmetry. So I'm going to do one more of these. The bromine is out here. The hydrogen's out here. And then if I flip it up, then now the bromine's going to be on a dash down here and on a wedge over here. And so, is this a plane of symmetry? No. But either you need to build the molecule or you need to draw that out and rotate before you can see this. So it is not meso. And so this has 2 stereocenters. We would just say it is chiral. Now, with that, I know I went kind of quickly with all of this, but thank you for your patience. Thank y'all for staying. For video watchers, thank you for watching. I'm about to be starting my office hours, and I can answer any other questions that you'll have during that. So thank you.